All right, so we're going to look at acids and bases and pH a bit here. We've looked a bit with our example pH indicator or acid-base indicator, and today we'll try to see a little more about acids. What are acids like? So if you think of acids, what types of things are you thinking of? Probably you think of maybe foods, lemon or manao, or sour fruits. That would be one, or citrus fruits. You might think of battery acid in car batteries. So what are acids? Oftentimes we start off by saying, well, what are they like? And so let's take a look at what they're like. So acids have a few common characteristics. One of them is that they usually have a sour taste. Then another thing that we usually see is that they can cause indicators to change color. So one example of an indicator that we use in the lab a lot, we have litmus paper. Litmus is a chemical that comes from a lichen, and when it has a very specific property that makes it so that we like it in the lab. So if I have an acid, it might change my litmus paper. So here I've got some vinegar, and I'm going to put my vinegar onto my red litmus paper. What do you think is going to happen when I do that? Okay, make a guess, and then let's see. Oh, is that what you guessed? It got wet. Right? Okay. So we see it got wet, but we don't see any change there. Okay? But litmus paper comes in two varieties. There's red litmus paper and blue litmus paper. If we're going to be honest, the red litmus paper is more like pink, and the blue litmus paper is more like purple. But here's my blue litmus paper. Well, we'll see. If I take that same vinegar and put it on the blue litmus paper, what's going to happen? Let me see. There we are. There's that change. So an acid can change blue litmus paper to red. That is the thing that lets us know that this is an acid. Okay? The thing that makes litmus paper so special is that the place where it changes is right exactly at neutral. So if you have something that's just a little bit acidic, it can change the color. Or if you have something that's just a little bit basic, it could change the color of the red litmus paper. Okay. So we'll come back to our litmus paper there. So acids, one of their characteristics is they cause indicators to change color or indicate in some other way. Acids tend to conduct electric current. They have the characteristic that we need to conduct electricity. And they are corrosive. They can burn or eat away at materials, different types of clothing, different type. Our flesh can be eaten away by acid. Metals can be eaten away by acid. If you ever put a metal spoon into lemon juice and left it for a while, you might find that in the end there's little pits in that spoon from the metal getting eaten away. One other characteristic that we see is that acids will tend to react with carbonates. So here I have sodium bicarbonate, or baking soda, and if I put a little bit of acid with that sodium bicarbonate. That would be the reaction that we're familiar with. Vinegar with baking soda, right? So it goes sizzle, 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 and there we are. Okay, so that this is used a lot of times in geology because one carbonate is calcium carbonate. Limestone or calcite is made up of calcium carbonate. So geologists often have a little bottle of hydrochloric acid that they keep with them and they take into the field. If they want to know if something is limestone, they drip a couple drops on and see if it starts fizzing like the baking soda does. All right, so those are things that are characteristics of acids. Well, how about bases? Lots of the things that are going to be characteristics of bases are just going to be the opposites of acids. One that's not exactly an opposite, but taste can be used to identify a base as well. If you have something that's a base, it usually has a bitter taste to it. If you've gotten soap in your mouth, that bitter taste comes from the basic nature of that soap. If you've ever had cookies or muffins that had too much baking soda put into them, and you take a bite, usually first it tastes real nice, and then you get that bitter taste that goes all through your mouth. So that would be one thing that is a characteristic of a base. They also can change the color of indicators. So again, here's my red litmus paper, and this time if I take my baking soda water and I put it on, what do we see? Oh, it goes from the red to the blue. Okay. So in the end, are these two separate things, the red litmus paper and the blue litmus paper? No, it's the same thing. It's just the red litmus paper starts out just a little bit acidic. The blue litmus paper starts out just a little bit basic, and then you can go from there. If you only had red litmus paper and you didn't have any blue litmus paper, you could put a little bit of base onto it, and then you could put an acid on that and change it back, or vice versa. If you have the blue litmus paper, you could put a little bit of acid onto it and turn it to pink or turn it to red, and then we put the base onto it and it turns it to blue, right? So, litmus paper is one example of an indicator, and it's one of the things that we see. When we talk about bases, you might think that we would say, well, okay, bases, they don't damage the skin, and they don't react with metals. But we don't say that because that's not true. When we have a strong base, it can also burn our skin, much like a strong acid can burn our skin. So you have to be careful with both bases and acids. So when we look at indicators, the litmus paper is not the only indicator that we have. We have other types of indicators as well. So we'll look at a couple of those here in a moment. So our acids, we have some acids that are strong acids and some acids that are weak acids. What's the difference between those strong acids and the weak acids? Okay, you might remember when we were talking about lab safety and I talked about hydrochloric acid, I said it's a strong acid. And even though we were working with dilute hydrochloric acid, we said, okay, dilute means you've got some time before it starts doing significant damage to your skin. But that doesn't mean, oh, this is just dilute, forget about it. I don't need to clean that off. I'll clean it off sometime when I'm washing up after my lab. It is a strong acid. Every one of those active ions in that solution is going to react with your skin. So strong acids are made up of some ions. Lots of times we might say acids have hydrogen ions. In our book, they like to talk about hydronium ions more so, but they're almost the same. So a hydrogen ion is an H positive, a hydrogen that's lost its negative electron. Hydronium is what we find is when these hydrogen ions are in solution, they tend to bind to water molecules. And so then we end up with an H3O positive, because we have the H2O plus the one H positive ion with it. And so they'll form hydronium ions. Okay? And then they've got something else. So like hydrochloric acid has that chloride ion along with the hydrogen ion or the hydronium ion. Acids, for something to be a true acid, it has to be a solution in water. So if I have HCl, usually we say that's hydrochloric acid. But if I had HCl that wasn't a solution, then it wouldn't be an acid yet. So those are strong acids. Then weak acids. So acetic acid, like my vinegar, is a weak acid. If I got vinegar onto my skin and it sat around for quite some time, I'd probably still be okay. Because not all of those acid compounds, let's say, not all those acid compounds are going to ionize, are going to separate into ions. So I'm going to get some that separate and make hydronium ions or hydrogen ions in water, but some of them won't. So they'll just stay together. Okay? So if you look at page 295 in your book, you might see some examples of some strong acids and some weak acids that they give there. And then, as we have talked about before, we have concentrated acids and dilute acids. And that doesn't necessarily tell you whether they're strong or weak, but a concentrated acid can damage very quickly. With our bases, many bases are going to form hydroxide ions when they're in water. So those are OH negatives. So OH negative ion. So one oxygen, one hydrogen. So I have some sodium hydroxide here, and sodium hydroxide is a strong base. It has those hydroxide ions in it. And then we have other things. The baking soda solution is a base, but it's not a strong base. It's more of a weak base. Ammonia is a common base. And other things, potassium hydroxide, calcium hydroxide, most of those hydroxides are going to be we'll look at that later. Okay. So then, one other thing that we often will hear is the term pH when we're talking about acids and bases. So what is pH? What is the pH of a solution? The pH of a solution is going to be something that can tell us how acidic or how basic a solution is. Okay? So, one thing that we saw here was that the base turned my red litmus paper blue. So that lets me know that it's a base. But this indicator here, it only tells me yes or no. Is it a base? Yes. But sometimes we want to know more than that. And when we talk about pH, oftentimes we see a rainbow shown alongside the pH scale. So here, why a rainbow? Well, it has to do with another indicator that we have. So universal indicator or universal pH solution. These universal indicators can show us how much acidic or how basic something is. Okay, so I have some Manal here, and if I get some of that juice and I put it on the end of my universal indicator paper, it turns it red. Okay, then if I take some of my vinegar and put that next to it, okay, similar but a little more orange. Okay. Then next to that, I'll put a bit of water. And the water doesn't give much change, a little bit greenish to it, but it's still fairly a greenish yellow. And my baking powder solution here, baking soda solution, I should say. That one turns it blue. Okay. And then my sodium hydroxide here, if I get a bit of that one on here, that one turns it purple. Okay. So in the end, I end up with a rainbow of colors. And they've done this, really what they've done is they have a number of different indicators that they mixed all together. And they change color at different pHs. So like our litmus changes right exactly at the middle where it goes from being acid to base. This one has a number of them that change at different pHs. So then we can get a rainbow of colors depending on which ones are which color at this time. Okay? And we want it to be even a little more certain here. This is another type of universal pH indicator paper. This one has 4 different little pieces of paper on the end of it, and if I put my solution on these, I can see what colors they turn, and then that one will help me to see what the pH of this solution is. Okay, so I look at this one and I say, I don't know which one this is. So this goes from 0, 1, 2, 3, 4, 5, 6, 7 on the front, and then from 7 all the way up to 14 on the back. So I follow these up and I look at them, and it's darker than this, darker than this, darker than this. They're starting to get close. So this one looks like it's right at that 14. So this one is all the way at the end of the scale. So 13 to 14 is this sodium hydroxide solution that I have. Okay, so so this one, it gives us a little more certainty than the colors of the rainbow do, because we can see with more certainty each of these 4 different ones, what color they are. Okay. So then this is pH, and pH is actually measuring how much hydronium, or what the concentration of those hydrogen ions are. So you might note that it's kind of funny. There's a lowercase p and then an uppercase h. The H is for hydrogen. So what's the concentration of hydrogen ions? And when we're looking at this, the pH is the negative, how many, it's like when we have the decimal point, how many zeros do I go to show the concentration of that of those hydrogen ions in there? Okay, so if it's 0.0000, then that would be a pH of 5. And so that's why we get kind of an unusual thing that as it gets more and more acidic, the numbers are going to go lower and lower. So something that has lots of hydroxide ions, but very little hydrogen ion, is going to be, like number 14, because that means we have a decimal point and then we have to go 14 places before we find the 1. So 0.00000000000001. So if we have one, if we go all the way up to concentrated, we're going to get 0, meaning I need to go 0 decimal places to find the concentration of that hydrogen ion. Okay, so so that is something that we can look at. That's just one thing that I'd like you to see, because pH can be confusing sometimes. What does it actually mean? And why is it that something that's so acidic, such a strong acid, has a low number like 0, and something that's neutral, like water, is at 7, and how come when we get to the strongest bases, we're up at high numbers like 14?